Imagine, if you can, a moment before moments existed, before light, before time, before the very fabric of reality as we know it unfurled. What was there? Or perhaps a better question, when was there? Because before implies a timeline, and at this extreme boundary of existence, even time becomes a shaky concept. This is the realm of cosmology's most profound mystery, the instant, or perhaps the non-instant, preceding the Big Bang. We call it a singularity, but that's just a word, a label we use when our current understanding of physics hits a wall. Think of it like this. Imagine trying to describe the color blue to someone who has only ever seen shades of gray. Our language, our mathematics, our very ways of thinking are rooted in the universe that exists after this point of origin. So describing what came before becomes almost an exercise in futility. It's like trying to catch smoke with your bare hands. But that doesn't stop us from trying. Scientists, armed with equations and fueled by relentless curiosity, are pushing the boundaries of what's knowable. They're grappling with concepts that sound like science fiction. Alternate dimensions, quantum foam, a multiverse bubbling with infinite possibilities, each a potential player in this cosmic drama. The singularity as we understand it represents a point of infinite density and temperature, all the matter and energy of the observable universe compressed into a space smaller than an atom. The laws of physics as we know them simply break down. Einstein's theory of general relativity, which so elegantly describes gravity and spacetime, falters. Quantum mechanics, the bizarre world of subatomic particles, offers glimpses of possibilities, but it too struggles to paint a complete picture. So, what could possibly ignite such an explosive origin? What conditions could coalesce to create a universe from seemingly nothing? Some theories propose a collision of brains, multidimensional objects existing outside our familiar three spatial dimensions. Others suggest a quantum fluctuation, a random blip in the nothingness that somehow, against all odds, triggered the Big Bang. Physicist Stephen Hawking famously argued that because time itself began with the Big Bang, the concept of before is meaningless. Asking what came before the Big Bang, he said, is like asking what is north of the North Pole. Consider the sheer audacity of the question. We are, as Carl Sagan once put it, star stuff contemplating the origin of star stuff. It's a journey into the unknown armed with only our intellect and our instruments. And perhaps, just perhaps, we are beginning to catch faint glimmers of understanding. We may never fully unravel the mystery of what came before, but the pursuit itself is pushing the boundaries of human knowledge, forcing us to confront the very limits of our understanding. This is the ultimate cold case, a cosmic whodunit with the entire universe as its potential culprit. The clues are subtle, the evidence elusive, but the stakes couldn't be higher, nothing less than the complete story of existence. And so from the precipice of the unknowable, we find ourselves poised on the very edge of creation. Imagine the universe emerging not as a gentle dawn, but as an instantaneous, incandescent explosion, a firestorm of unimaginable power unleashed from a point smaller than any conceivable subatomic particle. The Big Bang. This isn't the empty void of space we know today. This is something far more primordial, a superheated, infinitely dense soup of pure energy. Picture a pressure cooker cranked up to 11, then 11 again, and then to a level beyond any earthly comparison. It is from this extreme state that everything we know, everything we are, will spring forth. But what happened in those first fleeting moments? The instant time began its relentless march forward. The universe underwent a phase change of truly cosmic proportions. Energy began to coalesce, to condense, like steam transforming into liquid water. Only instead of water, fundamental particles began to flicker into existence. Quarks, leptons, the very building blocks of matter, materialized from the seething energy. And as they did, the fundamental forces of nature began to separate. Gravity, the force that binds planets and stars, was the first to peel away. Then came the strong nuclear force, which holds atomic nuclei together, followed by the weak nuclear force, responsible for radioactive decay, and finally, electromagnetism, the force behind light and all electronic interactions. It's like watching a kaleidoscope shatter, each fragment becoming a distinct and powerful entity. Think of it. In a time shorter than any word you could possibly speak, the rules of the universe were being written. The laws of physics, as we understand them today, were being forged in the crucible of the Big Bang. It's a cosmic recipe being perfected in real time, the ingredients being stirred together with unimaginable force. However, this beautifully simple picture of the Big Bang immediately encounters some rather inconvenient truths. It's like discovering a major plot hole in your favorite movie. While the standard model of the Big Bang explains much, it also leaves some crucial questions unanswered, some fundamental inconsistencies that simply cannot be ignored. Why, for instance, is the universe so remarkably uniform? When we look out into the cosmos, we see that distant regions that have never been in contact with each other, are strikingly similar in temperature and density. It's as if they somehow coordinated their evolution, a feat that seems impossible given the speed of light limitations. It's like finding identical fingerprints on opposite sides of the universe. And then there's the question of flatness. The universe appears to be geometrically flat, meaning that parallel lines will remain parallel forever. But according to the standard Big Bang model, the universe should have significant curvature, either positive like a sphere or negative like a saddle. The observed flatness requires an incredibly precise set of initial conditions, a level of fine-tuning that borders on the miraculous. It's like balancing a pencil perfectly on its tip and expecting it to stay that way for eternity. Finally, where are all the exotic particles? The standard Big Bang predicts the existence of heavy, stable particles like magnetic monopoles, which should have been produced in abundance in the early universe. Yet despite decades of searching, not a single one has ever been detected. It's like planning a massive party and finding that all the guests have mysteriously vanished before it even begins. So, while the conventional Big Bang model paints a compelling picture of the universe's earliest moments, it's a picture with significant gaps, with puzzling anomalies that demand explanation. It's a theory that works to a point, but it leaves you wondering, why did the universe evolve the way it did? Why these particular properties? What critical piece of the puzzle are we missing? It's time to search for new ideas. Are we ready? But even as we marvel at the fiery birth of everything, a nagging doubt begins to creep in. It's a cosmic conundrum that threatens to unravel the elegant tapestry of the standard Big Bang theory. Imagine the universe as a vast, empty stage, billions of light years across. Now picture two actors standing at opposite ends, never having met, never having communicated, yet somehow wearing identical costumes and reciting the same lines. That, in essence, is the horizon problem. How is it possible that distant regions of the universe, regions so far apart that light, the fastest thing in existence, hasn't had time to travel between them, exhibit such remarkable uniformity? We peer into the furthest reaches of space, observing the cosmic microwave background radiation, the afterglow of the Big Bang, and what do we find? A remarkably consistent temperature varying by only minuscule fractions of a degree. It's like discovering that every single grain of sand on two separate beaches, thousands of miles apart, is the exact same size and shape. The standard Big Bang model struggles to explain this. It posits that the universe expanded from an incredibly hot, dense state, but at a rate that simply doesn't allow for distant regions to have interacted and reached thermal equilibrium. Think of it like 2 cups of coffee, one hot, one cold, placed on opposite sides of a room. Without any means of heat transfer, they'll remain at different temperatures. So how did the universe manage to achieve such a uniform temperature across its vast expanse? The answer, according to the standard Big Bang, is that it shouldn't have. It's a bit like finding a perfectly formed snowflake on a scorching summer day. It defies expectation. It challenges our understanding of the fundamental laws of nature. The uniformity we observe implies a connection, a shared history, a period of interaction that the standard Big Bang simply cannot account for. It's as if the universe is whispering a secret that challenges the very foundations of our cosmological understanding. Imagine the early universe as a chaotic sea of particles constantly interacting and exchanging energy. Over time, this interaction would lead to a uniform distribution of energy, a state of thermal equilibrium. But for this to happen, the particles must be able to see each other, to exchange information. And in the standard Big Bang model, the expansion of the universe is so rapid that distant regions effectively become invisible to each other, separated by horizons beyond which no communication is possible. It's like trying to conduct a symphony orchestra with the musicians scattered across different continents, unable to hear each other play. This uniformity is not just a minor detail, it's a fundamental aspect of the universe we observe. It's the foundation upon which galaxies, stars, and ultimately life itself are built. Without this initial uniformity, the universe would likely be a vastly different place, a chaotic and inhospitable realm devoid of the structures we see today. So the horizon problem is not just an academic curiosity, it's a question that strikes at the very heart of our understanding of cosmic origins. How could thermal equilibrium be achieved across such vast, causally disconnected distances? The universe seems to be telling us that something is missing from the story, that there's a crucial piece of the puzzle that we haven't yet found. Could it be a new force, a new particle, or perhaps a radical revision of our understanding of space-time itself? Whatever the answer may be, it's clear that the horizon problem represents a significant challenge to the standard Big Bang, a challenge that demands a bold and innovative solution. It pushes us to consider if everything we thought we knew about the early universe might only be part of a grander, more perplexing picture. We've seen how the universe's uniformity presents a major hurdle for the standard Big Bang theory, but that's not the only cosmic curveball. Imagine tossing a ball into the air. If you throw it upwards with too little force, gravity wins and it falls back to Earth. Throw it with too much force and it escapes Earth's gravity altogether, soaring off into the endless void. Now, imagine that ball is the universe itself, and the force is its expansion. According to Einstein's theory of general relativity, the universe's fate hinges on a delicate balance between its expansion rate and its density. If the universe was born with too much matter and energy, gravity would have ultimately triumphed, pulling everything back together in a big crunch, a reverse Big Bang. If, on the other hand, it had too little, the universe would have expanded too rapidly, becoming cold and desolate, with matter too diluted to form stars and galaxies. The mind-boggling thing is, our universe seems to exist right on the knife's edge, perfectly balanced between these two extremes. It's geometrically flat. Think of it this way. Imagine drawing two parallel lines on a piece of paper. If that paper is perfectly flat, those lines will extend infinitely, never converging or diverging. Now imagine drawing those same lines on the surface of a sphere. They would eventually converge, meeting at the poles. Conversely, on a saddle-shaped surface, they would diverge. Our universe, as far as we can tell, resembles that flat piece of paper. Distant galaxies appear to obey the rules of Euclidean geometry, the geometry we all learned in high school. But this flatness is incredibly surprising. According to general relativity, any initial curvature the universe possessed should have been dramatically amplified over billions of years of expansion. Any deviation from perfect flatness, no matter how small, would have grown exponentially. It's like a small crack in a dam, which over time widens into a catastrophic breach. So, the fact that we observe a flat universe today implies that the early universe must have been extraordinarily, almost unbelievably, flat. It's like hitting a bullseye on a dartboard from across the galaxy, an accuracy that seems impossible without some kind of cosmic guidance. How precise are we talking? Scientists estimate that the density of the early universe had to be fine-tuned to within 1 part in something like 1 quadrillion, that is 1 followed by 15 zeros, to achieve the flatness we see today. That's akin to saying if you fired a cannonball from Earth, you would want to be able to hit a coin sitting on the surface of Mars. This presents what cosmologists call the flatness problem. Why is the universe so flat? What mechanism could have possibly fine-tuned the initial conditions with such incredible accuracy? It's as if the universe were set up with a preordained destiny, a destiny that required an almost impossible level of precision from the very beginning. Some might even call it a miracle. Without some kind of explanation, the observed flatness of the universe seems to require an incredibly precise and frankly unnatural set of initial conditions. It begs the question, why didn't the universe either collapse back on itself in a fiery implosion or expand so rapidly that it became a cold, empty void? Why this delicate balance, this perfect flatness? Is it simply a cosmic coincidence, a lucky roll of the dice? Or is there something deeper at play, some fundamental principle that we have yet to understand? Maybe a force that we can't even imagine and have yet to discover. These are the questions that continue to drive cosmological research, and they push us to consider whether everything we thought we knew about the cosmos might only be scratching the surface of a deeper, far stranger reality. And so, the universe balances precariously on the edge of a knife, exhibiting a flatness that defies explanation. But the mysteries of the early cosmos don't end there. Imagine attending a grand ball, a celebration of creation, and expecting to see certain guests, certain exotic revelers predicted by the guest list itself. But as the night wears on, you realize that some of the most anticipated attendees are conspicuously absent. That, in essence, is the relic problem. The Big Bang Theory, in its standard formulation, predicts the existence of a zoo of exotic particles born in the incredibly high-energy environment of the early universe. These aren't your everyday protons and electrons. We're talking about super-heavy, stable particles like magnetic monopoles, hypothetical objects possessing only a single magnetic pole, either north or south, unlike ordinary magnets which always have both. Now, according to the physics of the Big Bang, these magnetic monopoles should have been produced in vast quantities, a veritable army of these exotic entities populating the early cosmos. They were almost guaranteed to be produced, inevitable remnants of the primordial soup. They were practically invited to the party, yet they never showed up. Despite decades of searching, using everything from giant underground detectors to satellite-based experiments, not a single magnetic monopole has ever been definitively detected. It's as if they vanished into thin air, leaving cosmologists scratching their heads and questioning the validity of their theoretical models. The universe, it seems, is playing a cosmic game of hide-and-seek, and these monopolies are proving to be exceptionally good at hiding. But where did they go? Were they never created in the first place? Or did something happen in the early universe to eliminate them, to sweep them under the cosmic rug? Perhaps they decayed into something else, something even more exotic and undetectable. Or perhaps, just perhaps, our understanding of particle physics at these extreme energy scales is incomplete. Maybe something happened to the monopole right after creation, causing it to decay quickly into lighter particles. The absence of magnetic monopoles and other predicted relics poses a significant challenge to the standard Big Bang model. It suggests that there's a missing piece of the puzzle, a crucial ingredient that we haven't yet accounted for. It's like discovering a crime scene with no apparent motive and no clear suspect. The evidence points to a certain scenario, but key elements are missing, preventing us from drawing a definitive conclusion. One could compare it to expecting a certain number of cookies from a recipe, only to find that most of them are gone when you open the oven. Did someone sneakily eat them, or did the recipe somehow prevent them from forming in the first place? Similarly, the universe's failure to produce the predicted number of magnetic monopoles forces us to reconsider our understanding of the very early cosmos. The fact that we are not stumbling over these magnetic anomalies today highlights a gaping hole in our current understanding. This mystery demands explanation, pushing us to explore new and potentially revolutionary ideas about the origins of everything. And so, the universe balances precariously on the edge of a knife, exhibiting a flatness that defies explanation. The fact that the universe is seemingly devoid of the exotic relics that should have been born during the Big Bang is also unexplainable based on the current information we know. But are we ready to simply throw our hands up and declare the standard Big Bang theory a failure? Absolutely not. Like a seasoned detective facing a perplexing crime scene, the scientific community wasn't ready to abandon the case. The Big Bang model, after all, gets so much right. It accurately predicts the abundance of light elements like hydrogen and helium in the universe. It provides a framework for understanding the formation of large-scale structures like galaxies and galaxy clusters. It's a story that resonates with observation, a compelling narrative of cosmic evolution. But, and it's a rather significant but, the unanswered questions, the inconsistencies, the flat-out weirdness we've uncovered simply couldn't be ignored. The horizon problem, the flatness problem, the relic problem, they all pointed to a single, undeniable conclusion. Something was missing. A crucial piece of the puzzle had yet to be found. A new ingredient was needed to reconcile theory with observation. It was like trying to bake a cake without flour or build a house without a foundation. The basic recipe was there, but it was incomplete, lacking a key element that would transform it from a promising concept into a fully realized reality. And so, cosmologists found themselves at a crossroads. The standard Big Bang theory, while successful in many ways, had reached its limit. It was a bit like an old map, accurate for a time, but no longer reflecting the true geography of the cosmos. Scientists realized that they needed to venture beyond the known, to explore uncharted territories of theoretical physics, to dare to imagine a universe far stranger and more wondrous than they had ever conceived. It was a time for bold ideas, for radical thinking, for a willingness to challenge long-held assumptions. The stage was set for a revolution, a paradigm shift that would forever alter our understanding of the universe and our place within it. The time for the old ideas was gone, and it was time for something new and improved. The universe, a puzzle box of epic proportions, has presented us with some seriously head-scratching anomalies. A remarkably uniform temperature across vast, causally disconnected distances, a geometry so flat it defies the odds, and a cosmic game of hide-and-seek with missing exotic particles. Were we staring at a dead end? Had the standard Big Bang theory led us astray? Not so fast. Sometimes the most elegant solutions are also the most radical. Imagine a doctor diagnosing a patient with a mysterious ailment. Traditional treatments have failed, and the symptoms persist. It's time to consider a bold new approach, a treatment that might seem unorthodox, even counterintuitive, but holds the potential to cure the underlying disease. This, in essence, is what happened in the world of cosmology. Enter inflation. No, we're not talking about rising prices at the grocery store. This is cosmic inflation, a mind-bending theory that proposes an incredibly brief period of exponential expansion in the universe's first fraction of a second. We're talking about an expansion so rapid, so violent, that it makes the Big Bang itself look like a gentle breeze. Picture this: the universe, in its infancy, undergoing a growth spurt of unimaginable proportions, expanding faster than the speed of light itself. It sounds like something straight out of science fiction, doesn't it? But bear with us, because this radical idea, primarily developed by the brilliant minds of Alan Guth and others, offers a truly elegant solution to the cosmic puzzles that have been plaguing cosmologists for decades. Now, you might be wondering, faster than the speed of light? Isn't that a violation of Einstein's theory of relativity? Well, not exactly. It's crucial to understand that it wasn't matter or energy moving through space faster than light. It was space itself, expanding at superluminal speeds. Think of it like this. Imagine an ant walking on a balloon. The ant can only walk so fast, but if you inflate the balloon rapidly enough, the distance between 2 points on the balloon can increase much faster than the ant's walking speed. It is the stretching of the fabric of reality itself that allows for these seemingly impossible speeds. So, what does this cosmic growth spurt actually achieve? How does it solve the horizon, flatness, and relic problems? Well, buckle up, because we're about to dive into some truly mind-bending concepts. It's akin to suddenly discovering that a simple ingredient added to that problematic cake recipe turns it into a masterpiece. Could this burst of growth be the missing piece? Could this be the key to unlocking the secrets of the early universe? The idea was gaining traction, the hope was rising, but the real question became, could it actually be true? So we've established that the universe underwent this mind-boggling period of rapid expansion, cosmic inflation. But what powered this incredible burst? What was the engine driving this exponential growth? Imagine trying to build a rocket without knowing about rocket fuel. You might have the frame, the design, but without the right propellant, it's just a static object. Similarly, the Big Bang model needed something, a fuel, if you will, to ignite this period of superluminal expansion. The answer, as far as our current understanding goes, lies in a hypothetical entity, the inflaton field. Now, this isn't your average field like the electromagnetic field or the gravitational field. It's what physicists call a scalar field, meaning it has a value at every point in space but no direction. Think of it like the temperature in a room. It's a single number at each location, not an arrow pointing in a specific way. It is everywhere, all at once, an unseen player in the cosmic drama. This inflaton field, in its earliest state, possessed an incredibly high potential energy density. Imagine it like a tightly wound spring brimming with stored energy, ready to unleash at any moment. This energy density acted like a temporary cosmological constant, a term in Einstein's equations that represents a uniform energy density permeating all of space. The best way to understand this is that the only thing that the inflaton knew was to expand and keep expanding. Now, a cosmological constant typically causes the universe to expand, but the inflaton field took it to a whole new level. Its energy density was so immense that it utterly dominated the universe, dwarfing the energy of all other particles and forces combined. It was the supreme ruler of the cosmos, dictating the terms of expansion. This dominance is why spacetime itself was forced to expand exponentially, inflating the universe from a subatomic speck to macroscopic scales in a tiny fraction of a second. Think of it like blowing up a balloon. As you pump air into the balloon, its surface area expands, but imagine if you could pump air into the balloon at an exponentially increasing rate, so that the surface area doubles with every breath. That's essentially what the inflaton field was doing to the universe, but on a scale that's almost impossible to comprehend. It's a rapid expansion of space-time, driven by the enormous potential energy of this scalar field. But why this particular field? Why did it have such a high energy density? Where did it even come from? These are questions that still plague cosmologists today. It's like finding a mysterious artifact with incredible power but no instruction manual. Its function is apparent, its origins are shrouded in mystery. Was the inflaton field a fundamental part of the universe's initial conditions? Was it a product of some even more exotic physics operating at energies beyond our current understanding? Perhaps it was a quantum fluctuation that grew to become an inflaton. Some theories suggest that the inflaton field might be related to the Higgs field, the field responsible for giving particles mass. Others propose that it's an entirely new type of field, one that interacts with gravity in a unique and powerful way. Ultimately, the true nature of the inflaton field remains one of the biggest open questions in cosmology. Yet, one thing is clear. This hypothetical field, with its immense potential energy, was the key to unlocking the universe's inflationary engine, setting the stage for the cosmos we observe today. Perhaps, as we continue to explore the universe, We might even find more answers than what we began with. It's a race against time to figure out one of the most complex events in history. So, the inflaton field, this mysterious entity, flooded the universe with its energy and set the stage for an incredible burst of expansion. But how do we even begin to wrap our minds around the sheer scale and speed of what happened next? We're not talking about a simple growth spurt. We are talking about something so extreme, so utterly beyond our everyday experience, that it requires us to completely recalibrate our understanding of the cosmos. Imagine a single-celled organism, something microscopic, invisible to the naked eye. Now picture that organism expanding to the size of our entire solar system in a time frame shorter than it takes for a light beam to cross a single atom. That, in essence, is what cosmic inflation achieved. In a tiny sliver of time, roughly between 10 to the minus 36th and 10 to the minus 32nd seconds after the Big Bang, the universe expanded by a factor of at least 10 to the power of 26. That is a 1 followed by 26 zeros. To even try to picture that is futile. To put it another way, consider a region of space smaller than a proton, far smaller than even the tiniest bacterium. During inflation, that region would have stretched to become larger than our entire observable universe today. It's like taking a single grain of sand and instantaneously transforming it into a beach that stretches to the edge of infinity. Think of a loaf of raisin bread. Before inflation, the raisins, representing early regions of density fluctuations, are packed closely together. Now imagine stretching that loaf of bread exponentially. The raisins, once neighbors, are now separated by vast distances, smoothed out across the expanding dough. Inflation acted like a cosmic baker, stretching the fabric of space-time and smoothing out any initial wrinkles or imperfections. It is like taking a deflated basketball and filling it with so much air that it becomes the size of Earth, all in the blink of an eye. What's perhaps even more mind-boggling is the speed at which all of this occurred. This wasn't a slow, gradual expansion. This was an explosive, almost instantaneous event. It happened so fast that it defies our intuition. Envision a film of water with ripples in it. Suddenly, that film is stretched so much that the wave that it makes is undetectable. The same can be said about the effect of inflation. It is this brief moment of rapid growth that helps us to understand the universe as we know it. We talk about light years as the measure of distances in space, but inflation acted on scales and at speeds that dwarf even those astronomical figures. This expansion happened in a fraction of a second, a time scale so infinitesimal that it's almost incomprehensible. It is the ultimate cosmic hyperdrive, a period of exponential expansion that transformed the universe in the blink of an eye. The effects of this rapid expansion would smooth out the universe to make it look perfectly flat. It would dilute the density of any exotic heavy particles that were in the early universe, removing any monopoles or hypothetical artifacts from the early universe. How could something so small expand so rapidly? This is something that is studied by scientists, physicists, and cosmologists to this day. Some may never know, but they are always trying to find the answer. It is something that has baffled scientists for years, and might be something that we will never understand. So, in a fleeting moment of cosmic history, the universe underwent a transformation of unimaginable scale, a period of hyperdrive expansion that shaped the cosmos we see today. But this raises a profound question. How can something expand faster than the speed of light? A question that is something scientists today seek to answer. So, in a fleeting moment of cosmic history, the universe underwent a transformation of unimaginable scale, a period of hyperdrive expansion that shaped the cosmos we see today. But this raises a profound question. How can something expand faster than the speed of light? It is a concept that seems to defy the very laws of physics, a paradox that has puzzled scientists for decades. The truth is, The phrase faster than light often conjures up images of spaceships hurtling through the galaxy, violating Einstein's most famous speed limit. But what we're talking about with cosmic inflation is something fundamentally different. It wasn't matter or energy surging through space at impossible velocities. It was space itself stretching, expanding, and growing at superluminal speeds. Imagine you're baking a pizza. You sprinkle some pepperoni evenly across the dough. Those pepperoni slices represent galaxies. Now you begin to stretch the pizza dough. The pepperoni slices themselves aren't moving across the dough any faster than you're pulling it, but the distance between them is increasing rapidly, much faster than the pepperoni are traversing the dough. That's a pretty apt analogy for what happened during inflation. The universe, the dough, was expanding, carrying galaxies, the pepperoni, along with it. Here's the crucial distinction. Einstein's theory of special relativity, the one that famously dictates nothing can travel faster than light, applies locally. It means that within a given region of spacetime, no object can overtake a beam of light. But general relativity, Einstein's theory of gravity, allows for spacetime itself to expand or contract at any speed. There is no speed limit on the expansion of space. It is like a cosmic loophole, a way for the universe to seemingly break the rules without actually breaking them. Think of it this way. Imagine you are an ant crawling on a rubber band. You can only crawl so fast relative to the rubber band itself. However, if someone stretches the rubber band, the distance between you and another ant will increase faster than either of you are crawling. Neither ant is breaking any local speed limits, but the overall expansion is superluminal. This may seem like a subtle distinction, but it's a crucial one. It means that inflation didn't violate Einstein's theory of relativity. It simply took advantage of a loophole in the cosmic code, using the expansion of space-time itself to achieve unimaginable growth in a tiny fraction of a second. The same theory that governs the motion of planets also governs the expansion of the universe. So, how can the very fabric of reality stretch faster than its own speed limit? It's a question that challenges our intuition, pushing us to the very edge of our understanding of space and time. Perhaps the universe in its infancy operated under different rules than the ones we observe today. Maybe the speed of light wasn't always a universal constant. Or perhaps our understanding of space-time is still incomplete, and there are hidden dimensions or forces at play that we haven't yet discovered. It is like saying maybe what we learned in school was completely incorrect. It's a cosmic paradox, a mind-bending twist in the story of the universe that continues to fascinate and challenge scientists around the world. How could something so fundamental seemingly be broken? What would this mean for our understanding of the universe? What secrets does it hold? The answers to these questions might just unlock the deepest mysteries of the cosmos and reveal the true nature of reality itself. It's a never-ending quest to find the truth, and perhaps the truth is stranger than anything we can imagine. So we've traversed the mind-bending landscape of superluminal expansion, a concept that challenges our very understanding of physics. But how does this cosmic hyperdrive actually solve some of the universe's most perplexing problems? How does it smooth out the wrinkles, so to speak? Let's tackle the flatness problem. Imagine you have a crumpled sheet of paper. It's full of curves, folds, and irregularities. Now imagine stretching that sheet of paper, pulling it outwards in all directions with immense force. What happens? The wrinkles begin to flatten out. The curves become less pronounced. The paper becomes increasingly smooth. That, in essence, is what inflation did to the universe's geometry. The universe, before inflation, might have been a chaotic mess of curves and warps, a cosmic funhouse mirror reflecting a distorted reality. But the exponential expansion of inflation stretched out those curves, smoothed out those warps, and flattened the universe's geometry to an almost perfect degree. This is something that can be witnessed by viewing the CMB or cosmic microwave background. Think of it like inflating a balloon. As you blow air into the balloon, its surface area increases, and any wrinkles or imperfections on the surface are smoothed out. The bigger the balloon gets, the flatter its surface becomes. Inflation acted like a cosmic balloon pump, inflating the universe to such an enormous size that any initial curvature was effectively erased. This is no small feat. As we discussed earlier, the observed flatness of the universe requires an incredibly precise set of initial conditions, a level of fine-tuning that borders on the miraculous. Without inflation, we would have to invoke some kind of cosmic coincidence to explain why the universe is so flat. It would be like saying that a dropped ball will stay in midair for eternity. But inflation provides a dynamic explanation, a natural mechanism for achieving this flatness. It doesn't require us to fine-tune the initial conditions to an absurd degree. It simply says that whatever the initial curvature of the universe may have been, inflation would have smoothed it out. It's like saying that it is okay to make mistakes, because in the end, everything will be okay. The best way to illustrate this is to see it in action. With the help of modern-day space exploration, many probes have been sent into space and have recorded this effect for themselves. Now, some might argue that this is just a theoretical construct, a mathematical trick designed to solve a specific problem. But the beauty of inflation is that it makes testable predictions. It predicts that the universe should be almost perfectly flat, and that's exactly what we observe. This observation is an important observation to further continue research for the world we live in. Cosmological measurements, particularly those gleaned from the cosmic microwave background, strongly suggest that the universe is indeed spatially flat. The precision is astonishing, and it aligns perfectly with the predictions of inflation. It's like finding a key that perfectly fits a lock, a piece of evidence that strongly supports the theory. So inflation not only solves the flatness problem, but it also provides a dynamic explanation that is consistent with our observations. It's a win-win scenario, a triumph of theoretical physics that has revolutionized our understanding of the universe. What other benefits will the theory of inflation produce? What other things will scientists discover? Well, that is something that will have to be answered some other time. So, the universe, having been stretched flat like pizza dough, might still leave you with one nagging question. If inflation separated everything so dramatically, how can we explain the remarkable uniformity we observe across the vast cosmos? It's a bit like this. Imagine a group of friends all sharing the same inside joke. How did they all get on the same page if they haven't been in contact for years? The answer, as it turns out, lies in understanding what happened before the inflationary fireworks began. Before the universe ballooned to unimaginable proportions, regions that are now separated by billions of light years were once incredibly close, snuggled together in a space smaller than a proton. It's a concept that stretches the mind, isn't it? Before inflation kicked in, these regions were causally connected. They were close enough to interact, to exchange energy, to reach a state of thermal equilibrium. Imagine it like a small pot of water simmering on a stove. The heat distributes evenly throughout the water, ensuring that every drop reaches the same temperature. In the early universe, before inflation, everything was in contact. It could achieve thermal equilibrium and uniformity. Now here's where inflation works its magic. This period of exponential expansion took that small, uniform region and stretched it to enormous scales, far beyond the reach of light to traverse in the time since the Big Bang. This is what solves our horizon problem. These regions might be vastly separated today, but they share a common origin, a shared history of thermal equilibrium. It's like those friends who once shared an inside joke that has never been forgotten, even after all this time. Inflation essentially took a small, well-mixed room and blew it up into a stadium. The air in the stadium remains uniform because it all came from the same source, the same initial conditions in that small room. The same thing applies to the CMB and cosmic uniformity as we see it in the sky today. Think of it like a cosmic Xerox machine. Inflation took a tiny, uniform patch of the early universe and duplicated it across vast distances, creating the large-scale uniformity we observe today. The same small ripple in the CMB is now stretched out across the whole sky. In fact, it is the very nature of the expansion that solves the horizon problem. Let's put it another way. Imagine you have a perfectly smooth canvas. You dip your brush into a single color and paint a small circle. Now imagine stretching that canvas, exponentially increasing its size. The circle of paint will spread across the canvas, eventually covering a vast area with a single uniform color. That's essentially what inflation did to the early universe, spreading uniformity across the cosmos. So inflation doesn't just smooth out the wrinkles in space-time. It also explains why the universe is so remarkably uniform, even across regions that should never have been in contact. It's a testament to the power of exponential expansion, a cosmic trick that solves one of the biggest mysteries of the Big Bang. But what happened to any other exotic matter that was in the universe as well? Was it lost in this expansion as well? That is something that might surprise you. So inflation doesn't just smooth out the wrinkles in space-time and explain the universe's remarkable uniformity, but what about all those pesky exotic particles predicted to exist in the early universe? Remember those magnetic monopoles? Those theoretical particles with only one magnetic pole, north or south? The ones that should have been as common as cosmic dust, but remain stubbornly absent from our observations. Were they simply lost in the shuffle? Were they pushed out of existence by the sheer force of inflation? The answer, it turns out, is both simpler and more profound. Imagine you have a room filled with ping-pong balls. Each ball represents a magnetic monopole. Now imagine expanding that room to the size of the Earth. What happens to the density of ping-pong balls? They become incredibly sparse, spread so thinly that finding even one would be a monumental task. That, in essence, is what inflation did to magnetic monopoles and other unwanted relics of the early universe. The exponential expansion diluted their density to virtually zero. Any monopoles formed before or during the earliest stages of inflation would be spread so thinly across the vastly expanded volume that finding one today is extraordinarily unlikely. It's akin to taking a single grain of sand and scattering it across the entire Sahara Desert. Good luck finding that. Think of it like cleaning a house. You might have dust bunnies hiding under the furniture and cobwebs clinging to the ceiling. But if you were to suddenly expand the house to the size of a galaxy, those dust bunnies and cobwebs would become so diluted that they would be practically undetectable. Inflation effectively cleaned the cosmic slate, sweeping away the unwanted remnants of the early universe. The Big Bang model predicted their existence. Inflation politely showed them the door. This isn't just a convenient way to get rid of unwanted particles. It's a natural consequence of exponential expansion. The volume of the universe increased by such an enormous factor that the density of anything that wasn't being actively produced, like the inflaton field itself, would have been driven to near zero. It's like making orange juice. If you use one orange for 1 gallon of water, the taste is quite strong. But if you were to use one orange for an ocean of water, you might not even taste any hint of orange. Now, you might be wondering, if inflation diluted everything so thoroughly, how did any matter survive at all? How did we end up with the galaxies, stars, and planets that we see today? The answer to that lies in the way inflation ended, a story for another time. The dilution of relics is a crucial piece of evidence supporting the inflationary paradigm. It explains why we haven't found any magnetic monopoles or other exotic particles predicted by the standard Big Bang model. It is like someone leaving an important clue behind. The existence of such a missing piece shows a link in understanding the universe around us. It's a cosmic disappearing act, a testament to the power of exponential expansion. So inflation didn't just smooth out the universe and make it uniform. It also cleaned up the cosmic mess, removing the unwanted debris of the early universe. It's a bit like Marie Kondo for the cosmos, tidying up the universe and leaving it ready for the formation of galaxies and, eventually, life. It created the perfect clean slate to start from and create planets, stars, and even life as we know it. What could possibly top that? So inflation didn't just smooth out the universe and make it uniform. It also cleaned up the cosmic mess, removing the unwanted debris of the early universe. It's a bit like Marie Kondo for the cosmos, tidying up the universe and leaving it ready for the formation of galaxies and, eventually, life. It created the perfect clean slate to start from and create planets, stars, and even life as we know it. What could possibly top that? The answer might surprise you. Because while inflation may have created this seemingly pristine cosmic canvas, it also, paradoxically, planted the seeds of everything we see around us today. Can you believe it? The same process that made the universe so uniform, so featureless, also gave rise to the galaxies, the stars, the planets, and ultimately, us. How is that possible? How could something that smoothed everything out also create the very structures we observe? The key lies in the quantum realm, in the strange and unsettling world of uncertainty that governs the behavior of particles at the smallest scales. Even during inflation, when the inflaton field was dominating the universe and driving its exponential expansion, it wasn't perfectly uniform. There were tiny, minuscule fluctuations, quantum jitters in the field itself. They are the inherent uncertainties in the inflaton field. The inflaton was always subject to the laws of quantum mechanics. Think of it like this. Imagine a perfectly still pond. On the surface, it seems smooth and undisturbed. But if you zoom in close enough to the molecular level, you would see that the water molecules are constantly jiggling, vibrating, and interacting with each other. These tiny fluctuations are always there, even in the most seemingly peaceful environments. That is exactly what happens in the quantum world. These quantum fluctuations in the inflaton field were incredibly small, almost unimaginably small. But during inflation, they were stretched to enormous scales, amplified by the exponential expansion of the universe. It is like blowing a bubble. Tiny imperfections in the soap film stretch across its entire surface and become visible as swirling patterns. These minute density variations became the gravitational anchors around which galaxies and clusters later formed. Regions with slightly higher density attracted more matter through gravity. These regions gradually grew over billions of years, eventually collapsing under their own weight to form the structures we see today. This means everything around us, from our Earth to our Sun to the Milky Way galaxy, and so on. We owe our existence to these quantum ripples. Without them, the universe would be a smooth, featureless void, devoid of any structure. It is because of these tiny quantum fluctuations that the universe has structure today. They are the seeds of galaxies, the foundation upon which the entire cosmic web is built. Our solar system, our planet, our very selves, are a consequence of these quantum jitters being stretched to a massive scale. This is a truly profound realization. It means that the seeds of cosmic structure were sown not in some grand, deliberate act of creation, but in the random, chaotic fluctuations of the quantum realm. It's a cosmic irony. The quantum realm is so foreign to us, but has a massive impact on our daily lives. Our existence is predicated on a completely random event. Think about that for a moment. The galaxies, the stars, the planets, everything we see around us ultimately arose from these tiny quantum uncertainties. Without that, it would have been almost impossible for life to arise. It makes one question the very nature of the universe and what our true purpose is in life. Perhaps it means nothing at all. It is a humbling thought, a reminder that we are all connected to the universe in ways that we are only beginning to understand. The ripples in the CMB is not just a piece of theoretical knowledge, but the true foundation of life. It makes one question whether it's all just chance, or whether there is actually a true maker. So inflation didn't just smooth out the universe, it also planted the seeds for future structures, the seeds from which galaxies, stars, planets, and life itself would eventually arise. But how did inflation come to an end? And what happened to all that energy stored in the inflaton field? What was to happen to the very event that made our existence possible? So inflation didn't just smooth out the universe. It also planted the seeds for future structures, the seeds from which galaxies, stars, planets, and life itself would eventually arise. But much like an epic fireworks display, even the most spectacular show must eventually come to an end. The inflationary period, this fleeting but fundamentally important moment in cosmic history, couldn't last forever. What happens when the cosmic firework finally sputters and dies? Think of it like a runaway train. It can only continue at full speed for so long before it either runs out of fuel or derails. In the case of inflation, the derailment came in the form of the inflaton field finally reaching the bottom of its potential energy hill. Remember that tightly wound spring we talked about, brimming with potential energy? Well, imagine that spring finally unwinding, releasing all that stored energy in a burst. This is where the process known as reheating comes into play. It's not about warming up leftovers, mind you. This is a cosmic reheating, a transformation of energy that marked the transition back to the standard Big Bang expansion phase. The potential energy stored in the inflaton field, the very energy that drove the exponential expansion, didn't simply vanish. It decayed, transforming into a hot, dense soup of particles and radiation. Imagine a perfectly still body of water suddenly disturbed by a massive asteroid impact. The energy of that impact would ripple outwards, creating waves and turbulence, transforming the calm water into a chaotic maelstrom. Similarly, the decay of the inflaton field unleashed a torrent of energy, creating a primordial soup of quarks, leptons, photons, and all the other fundamental particles that make up our universe. It's like turning a dial. On one side, there's inflation, the universe stretching out at a rate faster than imagination allows. On the other, reheating, a transition to a new state where particles interact and take on their familiar characteristics. How did this transition truly occur? What allowed the inflaton to decay and create the next steps for our universe? These questions are pondered on a daily basis. This wasn't a gentle transition. It was a violent, chaotic event. The universe went from being dominated by the smooth, uniform energy of the inflaton field to being filled with a seething plasma of particles interacting at incredibly high energies. It's this event that truly marked the start of the hot Big Bang model that scientists had been working on for so long. Think of it as the moment when a caterpillar transforms into a butterfly, a complete transformation from one state to another. But why did the inflaton field decay? What triggered this transition? The honest answer is that we don't know for sure. It could have been triggered by quantum mechanical effects or by some unknown interaction between the inflaton field and other particles. Maybe it was something as simple as a change in energy. After all, that is what everything truly boils down to. Regardless of the exact mechanism, the end result was the same. The universe was reheated, filled with the raw ingredients needed to build galaxies, stars, and planets. Without this reheating process, the universe would have remained cold, empty, and largely featureless. It's like having all the ingredients for a cake, but never turning on the oven. It's important to realize that reheating wasn't just the end of inflation. It was also the beginning of something new. It marked the transition to the era when the standard Big Bang model takes over, the era when the universe cooled and expanded, allowing protons and neutrons to form, then atoms, and eventually stars and galaxies. It is the transition that allows for all these structures to exist today. So the graceful exit of inflation, the reheating of the universe, was a crucial turning point in cosmic history. It was the moment when the universe transitioned from a period of rapid expansion to a period of slower, more familiar expansion. It was the moment when the seeds of cosmic structure began to sprout. Could there be more? Could there be new questions to ask and answer? So, the graceful exit of inflation, the reheating of the universe, was a crucial turning point in cosmic history. It was the moment when the universe transitioned from a period of rapid expansion to a period of slower, more familiar expansion. It was the moment when the seeds of cosmic structure began to sprout. Could there be more? Could there be new questions to ask and answer? But hold on, because what followed the inflationary epoch might be even more astonishing. Imagine a cosmic oven set to broil, cranked up to temperatures that would make even the heart of a star seem like a cool breeze. What happens when that oven door swings open, releasing the pent-up heat and energy? That, in essence, is what we call reheating, the true beginning of the hot Big Bang. It wasn't just about cooling down. It was about igniting a new phase of cosmic evolution. Think of it less like a gentle sunset and more like a controlled explosion, a carefully orchestrated event that paved the way for everything that followed. It's an event that set the conditions for the universe as we know it today, an event that filled the cosmos with the very stuff we are made of. Following inflation's dramatic finale, the universe was far from empty. It was filled with the energy of the inflaton field, poised and ready to unleash its fury. Picture it as a cosmic reservoir, brimming with untapped potential, waiting for the moment to surge forth. This release of energy created the conditions described by the standard hot Big Bang model, the framework that scientists use to understand the universe's evolution. Without reheating, there would be no hot Big Bang, there would be nothing at all. It's like a conductor raising his baton, signaling the start of a symphony. Reheating provided the initial conditions, the starting point for the universe's thermal history. It established the rules of engagement for the particles and forces that would shape the cosmos in the eons to come. It's an event that makes one question the very foundations of reality. It allows one to ask questions such as, is time real, or is it simply a figment of our imagination? So, in a sense, inflation was the overture, the prelude to the main event. It set the stage for the hot Big Bang to proceed as we traditionally understand it. The energy released during reheating created the matter and radiation that we observe today. You may be asking yourself, how can this be? What is it that made our very existence possible? The answer may be easier than you think. Think about it. Before reheating, the universe was dominated by the inflaton field, a mysterious entity that we still don't fully understand. After reheating, the universe was filled with a hot, dense soup of familiar particles, quarks, leptons, photons, and more. These are the building blocks of everything we see around us, from the smallest atoms to the largest galaxies. It's like a potter taking raw clay and shaping it into a vase. Reheating transformed the energy of the inflaton field into the fundamental ingredients needed to build the universe. And while it may seem unbelievable, the very matter that we are made of came from the period of reheating. It's what truly allows us to question our very existence. But here's the really astonishing part. The energy released during reheating was not just any kind of energy. It was thermal energy, the energy of heat. This thermal energy heated the universe to unimaginable temperatures, trillions upon trillions of degrees. It's a temperature so extreme that it defies our everyday experience. It's a cosmic forge, a crucible where the raw materials of the universe were forged in the fires of creation. The energy created by reheating is the spark that allowed life to exist. The release of energy is something scientists can only dream of recreating. So, reheating wasn't just the end of inflation. It was the true beginning of the hot Big Bang, the event that set the stage for the universe we know and love. It was the moment when the universe transitioned from a period of rapid expansion to a period of cooling and condensation. It was the moment when the seeds of galaxies began to sprout and the building blocks of life began to assemble. Without reheating, everything would be different, or more likely, there would be nothing at all. It's because of this event that we are able to look at the stars today. It's because of this event that allows us to question reality. It's as if the universe was holding its breath during inflation and then finally exhaled, releasing a torrent of energy that kick-started the next stage of its evolution. It's what allowed the universe to continue and not collapse in on itself. The universe needed the constant release of energy in order to continue its evolution. Perhaps like the phoenix rising from the ashes, the hot Big Bang arose from the remnants of inflation. But, like any good origin story, the search for answers is far from over. The question becomes, are there echoes from this dawn that still reverberate through the cosmos today, waiting to be heard? But like any good origin story, the search for answers is far from over. The question becomes, are there echoes from this dawn that still reverberate through the cosmos today, waiting to be heard? How can we be so sure that inflation actually happened? Is it simply a beautiful theory, a mathematical construct that elegantly solves some of the universe's biggest problems, or is there concrete evidence to support it? Imagine searching for whispers from the very beginning of time. It sounds impossible, doesn't it? And yet cosmologists believe they have found just that. The key, incredibly, lies in something called the cosmic microwave background, or CMB. Think of it as the afterglow of the Big Bang, a faint echo of the universe's infancy. It's a bath of radiation that permeates the entire cosmos, a cosmic fossil that dates back to just 380,000 years after the Big Bang. That might sound like a long time ago, but in cosmic terms, it is practically yesterday. Now, this radiation isn't just a uniform glow. It has tiny variations in temperature, minuscule fluctuations that provide a snapshot of the conditions in the early universe. These temperature variations are incredibly faint, on the order of 1 part in 100,000. It's like trying to detect the heat from a single candle flame placed thousands of miles away. These fluctuations, seemingly insignificant, are a treasure trove of information about the universe's origins. They are an imprint of the conditions in the early universe, a fingerprint left by inflation itself. It is like reading a message in a bottle, or hearing a long-lost friend after many, many years. This fingerprint has the potential to unlock all of the secrets of the universe. But how can we be so sure that these fluctuations are related to inflation? What exactly are scientists looking for? Well, inflation makes very specific predictions about the properties of these fluctuations, predictions that can be tested against our observations. One of the most important predictions is that the fluctuations should be nearly scale invariant, meaning that they should have roughly the same amplitude on all scales. It is like hearing the same song on different radios. It should be clear no matter where you listen to it. This is because inflation stretched out those quantum fluctuations to such an enormous size that their original scale became irrelevant. It is important for the fluctuations to have a uniform sound, or else this means that our whole theory is wrong. It might feel like an insurmountable problem, something that scientists will struggle with for years to come. However, there is a light at the end of the tunnel. Think of it like ripples in a pond. If you drop a pebble into the pond, you will create ripples of all sizes. But if you were to somehow stretch the pond to an enormous size, the ripples would all become very long and stretched out, with roughly the same amplitude. This is an important aspect that ties everything together. Another prediction of inflation is that the fluctuations should be Gaussian, meaning that they should follow a bell curve distribution. This is a statistical property that arises from the random nature of quantum fluctuations. A Gaussian distribution is what is expected. Scientists fully expect that the results of this echo are going to follow this rule. It's like flipping a coin many times. You would expect to get roughly the same number of heads and tails, with small deviations from the average. The CMB could be something that ties together the universe in a neat package. These predictions are not just theoretical musings. They can be tested against observations of the CMB, made by satellites like COBE, WMAP, and Planck. The data from these missions have provided us with an incredibly detailed map of the CMB, revealing the subtle temperature fluctuations across the sky. Scientists meticulously study these maps, analyzing the statistical properties of the fluctuations, searching for the telltale signatures of inflation. It is akin to listening to a record for hidden messages. You might only catch the message if you know what to look for. And what have they found? The answer is, overwhelmingly, support for inflation. The CMB fluctuations are indeed nearly scale invariant and Gaussian, just as inflation predicted. This is a truly remarkable confirmation, a triumph of theoretical physics and observational cosmology. It's like finding the missing piece of a puzzle, a piece that perfectly fits into place and completes the picture. The implications of this data are profound. In the face of everything we have learned, what truly is the next question we must ask? Does the cosmic microwave background contain secrets still waiting to be revealed? But is it all just smoke and mirrors? Is inflation simply a theoretical house of cards built to solve a few cosmological puzzles, or does it stand on a foundation of solid evidence? The universe, it seems, has left us a message, etched in the very fabric of space-time itself. A message that cosmologists have been painstakingly deciphering for decades. We've talked about the cosmic microwave background, the CMB, that faint afterglow of the Big Bang. But what if I told you that this afterglow isn't just a uniform hum, but a complex symphony of temperature variations, a cosmic fingerprint that could unlock the secrets of the universe's earliest moments? It is truly a symphony of events that make it all come together. These aren't just any random fluctuations. Inflation makes very specific predictions about their statistical properties. It predicts that the temperature variations, or anisotropies, in the CMB should have a nearly scale-invariant spectrum. What does this actually mean? It means that the fluctuations should have roughly the same amplitude or intensity on all scales, from the largest to the smallest. Picture it like a musical scale, where each note, whether high or low, has approximately the same volume. Why is this scale invariance so important? Because it's a direct consequence of inflation's exponential expansion. During inflation, tiny quantum fluctuations were stretched to enormous scales, far larger than the size of the observable universe today. This stretching process diluted any pre-existing scales, resulting in a spectrum of fluctuations that is nearly uniform across all wavelengths. It is how music is able to have such a wide range of listeners. Think of it like blowing up a photograph. As you enlarge the photograph, the details become stretched and distorted, but the overall pattern remains the same. Inflation acted like a cosmic enlarger, stretching the quantum fluctuations and imprinting them onto the CMB with a nearly scale-invariant spectrum. But it's not just about scale invariance. Inflation also predicts that the CMB fluctuations should be Gaussian. Again, this is a statistical property that arises from the random nature of quantum fluctuations. A Gaussian distribution is what we would expect to see if the fluctuations were truly random and independent of each other. This is how we know that what we are seeing is not a hoax. Imagine throwing darts at a dartboard. If you are aiming randomly, the darts will tend to cluster around the bullseye, forming a bell-shaped curve. The CMB fluctuations should follow a similar pattern, with most of the fluctuations clustered around the average temperature and fewer fluctuations occurring at more extreme temperatures. These are bold predictions, but can they be tested? Can scientists actually measure the statistical properties of the CMB fluctuations and see if they match the predictions of inflation? The answer, thankfully, is a resounding yes. Over the past several decades, a series of increasingly sophisticated satellites, including COBE, WMAP, and Planck, have been launched into space to study the CMB in unprecedented detail. These missions have meticulously mapped the temperature variations across the sky, creating a stunning portrait of the early universe. These projects have each been successful. However, the future of the CMB is still bright. The James Webb Telescope might even catch more information and give a better understanding of the CMB. And what have they found? The data from these satellites have confirmed with remarkable precision that the CMB fluctuations are indeed nearly scale invariant and Gaussian, just as inflation predicted. It's as if the universe itself has whispered a secret code that can only be deciphered by the greatest minds that science has to offer. It is a beautiful image that leaves us pondering our place in the vast cosmos. The Planck satellite, in particular, has provided the most detailed map of the CMB to date, allowing scientists to measure the statistical properties of the fluctuations with incredible accuracy. The Planck mission has been able to determine the age of the universe. The mission also helped us to determine the mass of the universe. These measurements have not only confirmed the predictions of inflation, but they have also allowed scientists to constrain the parameters of inflationary models, providing valuable insights into the nature of the inflaton field and the dynamics of the early universe. It's almost as if scientists can see the blueprints to the creation of the cosmos. The consistency between the predictions of inflation and the observations of the CMB is a powerful piece of evidence supporting the inflationary paradigm. It's like finding a perfectly preserved fossil that confirms a long-held evolutionary theory. It means that the hard work and dedication of so many scientists has paid off, and that we are slowly and diligently discovering the secrets of the universe. But what does the flatness of the universe have to say on all of this? Does our new theory align with that as well? But what does the flatness of the universe have to say on all of this? Does our new theory align with that as well? Imagine drawing a triangle. Not just any triangle, mind you, but a massive one, with sides stretching across billions of light years. In a flat universe, the angles of that triangle would add up to precisely 180 degrees, the familiar rule we all learned in school. But if the universe were curved, like the surface of a sphere or a saddle, those angles would add up to more or less than 180 degrees. It's geometry on a cosmic scale. So how do we draw such a massive triangle? Well, we can't exactly use a protractor the size of a galaxy. Instead, cosmologists use the cosmic microwave background, the CMB, as their canvas. Those temperature fluctuations we've been discussing, those tiny variations in the afterglow of the Big Bang, aren't just randomly scattered across the sky. They exhibit a pattern, a characteristic angular size that depends on the geometry of the universe. It's kind of like using the stars themselves to create a cosmic map. Think of it like sound waves echoing through the early universe. These sound waves, technically known as baryon acoustic oscillations, were generated by the interplay between gravity and pressure in the primordial plasma. They created a pattern of hot and cold spots in the CMB with a characteristic size that is determined by the distance sound could travel before the universe became transparent. Now, if the universe is flat, those sound waves will appear to us with a certain angular size. But if the universe is curved, the light from those sound waves will be bent, altering their apparent size. It's like looking at a distant object through a lens. The lens can magnify or demagnify the object depending on its curvature. By carefully measuring the angular size of those hot and cold spots in the CMB, cosmologists can determine the geometry of the universe. It is a mind-blowing feat, using ancient light to determine the shape of the universe. And what have they found? The answer, once again, is overwhelmingly supportive of inflation. Modern cosmological measurements, particularly those from the Planck satellite, strongly indicate that the universe is spatially flat to within a very small margin of error. How small? Well, the measurements suggest that the density of the universe is incredibly close to the critical density, the density required for a perfectly flat universe. It is almost as if the universe is balanced on a knife's edge. This observation aligns perfectly with the predictions of inflation. In fact, inflation provides the most natural explanation for the observed flatness of the universe. Remember how inflation stretched out any initial curvature, smoothing out the wrinkles and leaving us with a nearly perfect flat cosmos? It is the same as inflating a balloon until its surface is essentially two-dimensional. The precise measurement of the universe's geometry provides compelling support for an early inflationary epoch. It's like finding the last piece of a jigsaw puzzle, a piece that completes the picture and confirms the overall design. It proves that what we have believed has been correct. But just how flat is flat enough to confirm the theory? Is there some wiggle room, some margin of error that would still be consistent with other theories? Well, cosmologists are continuing to refine their measurements of the universe's geometry, pushing the precision to ever higher levels. Every increase in precision allows for them to get better as scientists. The future generation of CMB experiments, such as the Simons Observatory and CMB Stage 4, promise to provide even more accurate measurements of the universe's geometry, further testing the predictions of inflation and potentially revealing new insights into the nature of the early universe. These instruments have the potential to provide a better understanding about where we came from and how it happened. So, while the universe may not be perfectly flat, like a geometric ideal, it is remarkably close to flat, close enough to provide strong evidence for inflation. It is truly a testament to how far we have come, a testament to the human ingenuity of all those scientists who never gave up. But hold on, because the story doesn't end there. The CMB isn't the only source of information about the universe's geometry. The distribution of galaxies and galaxy clusters across the cosmos also provides clues. What can they tell us? But hold on, because the story doesn't end there. The cosmic microwave background isn't the only source of information about the universe's geometry. The distribution of galaxies and galaxy clusters across the cosmos also provides clues. What can they tell us? Can the very arrangement of these celestial behemoths, scattered across billions of light years, somehow whisper echoes of the inflationary epoch? The answer, perhaps surprisingly, is a resounding yes. Imagine stepping back, way back, and viewing the universe not as a collection of individual galaxies, but as a vast, interconnected web. A sprawling network of filaments, sheets, and voids, with galaxies clustered along the threads like dewdrops on a spider web. This is the large-scale structure of the universe, the cosmic web, and it's a testament to the power of gravity acting on the seeds planted by inflation. These seeds, those quantum fluctuations we've discussed, weren't uniformly distributed. Some regions had slightly higher density than others, and over billions of years, gravity amplified those density differences. Think of it like a snowball rolling down a hill. It starts small, but as it gathers more snow, it grows larger and larger, eventually becoming a massive avalanche. Similarly, the denser regions in the early universe attracted more and more matter, growing into the galaxies and galaxy clusters we see today. The less dense regions, on the other hand, were left relatively empty, forming the vast cosmic voids. It's a cosmic dance of attraction and repulsion, a ballet of gravity played out across the expanse of spacetime. But here's the crucial point. The distribution of these galaxies and clusters isn't random. It mirrors the patterns we see in the cosmic microwave background. Those subtle temperature variations in the CMB correspond to the density fluctuations that gave rise to the cosmic web. It is a mirror image of what happened billions upon billions of years ago. Think of it like a blueprint. The CMB is the blueprint, the initial design, and the cosmic web is the finished product, the structure built according to that design. It's a remarkable confirmation of the inflationary paradigm, a demonstration that the same processes that shaped the early universe also shaped the large-scale structure we observe today. The CMB tells what happened, the cosmic web shows what it looks like today. Now you might be asking yourself, how do scientists actually map the distribution of galaxies across such vast distances? How do they create a three-dimensional picture of the cosmic web? It's a monumental undertaking requiring the combined efforts of astronomers and astrophysicists from around the world. The sheer scale of the project is almost unimaginable. They use powerful telescopes to observe the positions and redshifts of millions of galaxies. Redshift is a measure of how much the light from a galaxy has been stretched due to the expansion of the universe. The greater the redshift, the farther away the galaxy is. By measuring the redshifts of galaxies, scientists can determine their distances and create a three-dimensional map of their distribution. It's like creating a giant connect-the-dots puzzle, with each galaxy representing a dot and the cosmic web representing the lines that connect them. The end result is a breathtaking visualization of the large-scale structure of the universe, a testament to the power of gravity and the legacy of inflation. The effect is almost awe-inspiring when you finally see the final rendition. And the more detailed these maps become, the more closely they match the predictions of inflation. The size and shape of the cosmic voids, the distribution of galaxies along the filaments, even the subtle correlations between galaxy positions and CMB fluctuations all align with the inflationary paradigm. It would be impossible to make it all up, but perhaps the most profound implication of all this is that the very existence of galaxies, stars, planets, and ultimately life itself can be traced back to those tiny quantum jitters that arose during inflation. It is because of these quantum ripples that the universe has any structure at all. It makes one wonder what other mysteries the universe is hiding from us. These quantum jitters, amplified by the exponential expansion of inflation, provided the seeds for the formation of all the structures we see around us. It's like finding the very beginning of life itself. The ripples are the reason we are able to gaze upon the stars today. It's almost unfathomable to even imagine. So the next time you look up at the night sky, remember that you are not just seeing a random assortment of stars and galaxies. You are seeing the result of a long and intricate process that began in the first fraction of a second after the Big Bang. You are seeing the legacy of inflation, the amplified quantum fluctuations that shaped the cosmos and ultimately made our existence possible. These jitters are why we are able to think, to love, and to dream. It's a humbling and awe-inspiring thought, a reminder that we are all part of something much larger than ourselves. A cosmic web that connects us to the very origins of the universe. It begs the question, where do we go next? But what if there's more to the story? What if inflation, as successful as it is in explaining so much about the universe, isn't the only possible answer? Are there variations on the theme, alternative inflationary scenarios that could better fit the data? Or perhaps, even more radically, are there completely different theories that could explain the universe's earliest moments? So, we find ourselves standing at the precipice of cosmic understanding with a theory, inflation, that so elegantly explains so much about the universe. But what if inflation, in its current form, is not the whole story? What if, like a masterful musical composition, the inflationary epoch has multiple movements, variations on a central theme that reveal even deeper truths about our cosmic origins? The universe, after all, rarely offers simple answers. The story of inflation isn't a singular narrative etched in stone. Rather, it's a dynamic framework, a canvas upon which cosmologists are constantly painting new possibilities. Think of it like the theory of evolution. The basic principle of natural selection remains, but the specific mechanisms and pathways of evolution are constantly being refined and expanded. Similarly, inflation provides the broad strokes of the universe's earliest moments, but the details are still being hotly debated and intensely researched. Inflation isn't a singular theory. Instead, it is a category with many different models that may come up. These models vary on how they solve the horizon, flatness, and relic problems. It really comes down to what fits best with the data. One of the most intriguing of these variations is something called chaotic inflation. Developed by André Linde, chaotic inflation paints a picture of the early universe as a frothing sea of scalar fields, each with its own unique potential energy landscape. Think of it like a vast mountain range, with peaks and valleys representing different energy states. In some regions, the inflaton field might find itself perched high on a peak, possessing immense potential energy, driving exponential expansion. In other regions, it might be nestled in a valley, its energy depleted, resulting in a more sedate expansion. The beauty of chaotic inflation lies in its simplicity and generality. It doesn't require any special initial conditions or fine-tuning. It simply assumes that the universe began with a random distribution of scalar fields, and that inflation naturally occurred in regions where the inflaton field happened to be in a high-energy state. It is almost as if the universe takes the path of least resistance. But here's where things get truly mind-bending. Some inflationary models lead to the concept of eternal inflation. Imagine, if you will, that inflation isn't a one-time event, a fleeting moment in cosmic history, but a process that continues indefinitely in some regions of the universe. This may imply that our Big Bang was not unique. In eternal inflation, the universe is constantly spawning new bubble universes, each with its own set of physical laws and constants. Our observable universe would be just one of these bubbles, a tiny island in a vast, ever-expanding multiverse. It is almost as if our universe is one of many, each with its own story to tell. This concept raises profound questions about the nature of reality and our place in the cosmos. Are we alone in the multiverse, or are there countless other universes out there, some similar to ours, others radically different? Could there be universes where the laws of physics are so different that life as we know it would be impossible? Are these universes all that different, or are they more alike than what meets the eye? Eternal inflation is a highly speculative idea, and there is no direct evidence to support it. But it arises naturally from some of the most well-studied inflationary models, and it offers a tantalizing glimpse into the possibility of a multiverse far grander and more diverse than anything we can currently imagine. It does raise important questions and makes us question our very existence. These variations on the theme of inflation lead to potentially different observable consequences. Some models predict a slightly different spectrum of CMB fluctuations or a different level of primordial gravitational waves. Some models may even predict the existence of exotic particles or topological defects. Ultimately, the goal of cosmologists is to compare the predictions of these different inflationary models with observational data in order to determine which model best fits the reality of the universe. It's a bit like trying to solve a cosmic puzzle, with each model representing a different piece. Which version best fits the data? It is a question that continues to drive cosmological research. It pushes us to explore new and potentially revolutionary ideas about the origins of everything. It challenges us to confront the very limits of our understanding of the universe, and it reminds us that the story of inflation is far from over. It is a story still being written, with many more chapters yet to come. The secrets it holds may be stranger than anything we can imagine. But what about the inflaton field itself? Is it a fundamental particle? A messenger from a realm beyond our current understanding of physics? What role does it play in the grand scheme of things? But what about the inflaton field itself? Is it a fundamental particle, a messenger from a realm beyond our current understanding of physics? What role does it play in the grand scheme of things? Is it perhaps still playing that role even now, shaping not just our universe but countless others besides? Consider this. If inflation ended in our region of space-time, what's to say it ended everywhere? What if, in some far-flung corners of the cosmos, inflation continues unabated, a perpetual engine of exponential expansion? This is the tantalizing and frankly mind-blowing concept of eternal inflation. It is a question that has plagued the minds of many scientists today. Picture a vast ocean of space-time. In some areas, the water is calm, representing regions where inflation has ended and universes like ours have cooled and formed. But in other areas, storms rage, representing regions where inflation continues relentlessly, spawning new bubble universes like cosmic raindrops. In effect, there's no such thing as only one ocean. Instead, there might be countless. These bubble universes, each born from a pocket of eternally inflating space-time, might have vastly different properties than our own. The laws of physics, the fundamental constants, even the very dimensions of space-time could vary from bubble to bubble. It is as if each bubble is a new experiment, that is created from scratch. It begs the question, are we able to travel between these bubbles, or are we simply stuck in our own universe? Perhaps in some bubbles gravity is much stronger, leading to universes that quickly collapse in on themselves. In others, the electromagnetic force is weaker, preventing the formation of stars. And in still others, the cosmological constant is so large that the universe expands at an unfathomable rate, precluding the formation of any structure whatsoever. Are we then living in the Goldilocks universe, perfectly suited for life? Are we lucky to exist in a universe that is habitable? Are we the exception and not the rule? It would be impossible to know, as it would require scientists to be able to access those universes. The possibilities are truly endless, limited only by the imagination and the laws of physics, or rather, the varying laws of physics that might exist in these different universes. It is almost as if there are countless universes that have been created, only for them to die out shortly after. Now, this might sound like pure science fiction, but eternal inflation arises naturally from some of the most well-respected inflationary models. It's a consequence of the quantum nature of the inflaton field, the same field that drove inflation in the first place. It's almost hard to believe that one single field is the reason that we have so many questions today. Remember those quantum fluctuations, those tiny jitters in the inflaton field that seeded the structure of our universe? Well, in some regions of spacetime, those fluctuations can be so large that they actually prevent inflation from ending. These regions continue to expand exponentially, spawning new bubble universes ad infinitum. Think of it like a pot of boiling water. Bubbles constantly form and pop at the surface. But what if some of those bubbles were so large and so energetic that they broke free from the pot and became independent entities? That's essentially what happens in eternal inflation. It's easy to think of it as a cosmic fractal, a pattern that repeats itself at ever smaller scales. Just as a single snowflake contains the blueprint for an entire snowstorm, each bubble universe in the multiverse might contain the potential for an infinite number of new universes to arise. Are we then just one bubble in a cosmic foam? It's a question that challenges our very notion of what it means to exist and our place in the grand scheme of things. It calls into question whether what we think we know about the universe is even relevant. Perhaps our universe is not unique, not special, but simply one of countless others, each with its own unique history and destiny. Perhaps the laws of physics we observe are not universal constants, but simply local rules that apply only to our bubble. It's an idea that even theoretical physicist Stephen Hawking spent some time trying to figure out. It's a humbling and perhaps even unsettling thought, but it's one that cosmologists are grappling with as they continue to explore the implications of inflation. It forces us to question everything we thought we knew. What is real? What is reality? What if everything around us is simply a lie? These are tough questions to consider. The multiverse, if it exists, is likely beyond our ability to ever directly observe. The distances between bubble universes are likely so vast that no signal, not even light, could ever traverse them. It is something that may forever be out of reach. But that doesn't mean we can't explore the multiverse through theoretical models and indirect observations. By studying the properties of our own universe, by pushing the boundaries of physics to their limits, we can gain valuable insights into the nature of inflation and the possibility of other universes beyond our own. In doing so, perhaps we will discover the secret to all of creation. What about the inflaton field itself? Is it a fundamental particle, a messenger from a realm beyond our current understanding of physics? What role does it play in the grand scheme of things, and what is the relationship to the elusive and ever-intriguing dark matter and dark energy that make up the bulk of our universe? But what about the inflaton field itself? Is it a fundamental particle, a messenger from a realm beyond our current understanding of physics? What role does it play in the grand scheme of things, and what is the relationship to the elusive and ever-intriguing dark matter and dark energy that make up the bulk of our universe? Could understanding this infinitesimal moment unlock the greatest mysteries of time and space? The inflaton field, the driver of cosmic inflation, isn't just some abstract mathematical concept dreamt up by theoretical physicists. It represents a deep connection between cosmology, the study of the universe's origins and evolution, and high-energy particle physics, the exploration of the fundamental building blocks of matter and their interactions. It is the nexus between the infinitely large and the infinitesimally small. Think of it like this. Cosmology provides the big picture, the grand sweep of cosmic history, while particle physics delves into the microscopic realm, exploring the fundamental laws that govern the behavior of matter and energy. The inflaton field acts as a bridge between these two seemingly disparate fields, linking the universe's earliest moments to the fundamental properties of matter. It provides a glimpse of what it was like moments after the Big Bang. If we can truly understand the nature of the inflaton field, could that knowledge unlock new ideas about physics? Could it perhaps allow us to peer beyond the standard model, the highly successful but ultimately incomplete theory that describes the known fundamental particles and forces? The standard model, for all its triumphs, leaves many questions unanswered. It doesn't explain the origin of dark matter, the nature of dark energy, or the existence of neutrino masses. It is like knowing all of the notes on a musical scale, but not being able to assemble them into a cohesive song. Perhaps the inflaton field holds the key to unlocking these mysteries. Perhaps it's a window into a realm of physics beyond our current comprehension. The truth may be closer than we think. One of the most tantalizing questions is whether the inflaton field is related to the Higgs field, the field responsible for giving particles mass. The Higgs boson, discovered at the Large Hadron Collider in 2012, is the quantum excitation of the Higgs field. It is a fundamental cornerstone of the Standard Model. Could the inflaton be an even more fundamental element? Could the Higgs boson be related? Could the inflaton field be a heavier, more energetic version of the Higgs field? Or could it be an entirely different field, one that interacts with the Higgs field in some subtle but profound way? Perhaps the inflaton is an entirely new beast, something we have not even begun to comprehend. We may not even know it exists. The properties of the inflaton field, its mass, its interactions, its potential energy, are all linked to energy scales far beyond what current particle accelerators can probe. We are speaking of energies many trillions of times greater than those achieved at the Large Hadron Collider. It is like trying to build a skyscraper with only a hammer and a chisel. We need new tools, new technologies to explore these energy scales directly. This is where the cosmic microwave background, that faint afterglow of the Big Bang, becomes so crucial. It provides us with a window into the early universe, a snapshot of the conditions that existed when the inflaton field was driving inflation. By studying the patterns in the CMB, scientists can indirectly probe the properties of the inflaton field and test different theoretical models. The echoes of the Big Bang can tell us so much. The search for primordial gravitational waves, those faint ripples in spacetime generated during inflation, is a key part of this effort. Detecting these waves, potentially through their subtle signature, known as B-mode polarization, in the CMB, would provide definitive proof of inflation and offer valuable insights into the energy scale and dynamics of the inflationary epoch. The detection of these primordial waves is key to unlocking all of the secrets that the universe has to offer. The inflaton field, whatever its true nature may be, represents a profound link between cosmology and particle physics. It's a tantalizing suggestion that by understanding the universe's earliest moments, we can unlock secrets that have eluded us in our laboratories. It is a tantalizing path towards a deeper, more complete understanding of the fundamental laws of nature. It may even be the key to unlocking immortality. Perhaps the inflaton field is not just a relic of the early universe, but a fundamental ingredient of the cosmos, playing a role in the ongoing evolution of space-time and the emergence of new universes. Perhaps the answer to our questions lies in the very thing that brought our universe into existence. But with any great theory come certain challenges. Is the pursuit of the inflaton field a journey without end? Or will the cosmic whispers of the CMB reveal its true identity, opening doors to realms we can only dream of today? So, the quest to understand the universe's origins has led us to this mind-bending theory of inflation, a cosmic hyperdrive that shaped the cosmos in a fraction of a second. We've seen how it elegantly solves some of the biggest puzzles of the Big Bang, smoothing out the universe, making it uniform, and even planting the seeds for galaxies and life itself. But the scientific method demands more than just a pretty theory. It demands proof. What if there was a smoking gun, something that would unequivocally confirm that inflation actually happened? Imagine hunting for a ghost. You can't see it, touch it, or hear it directly, but you might find clues. A sudden drop in temperature, objects moving on their own, or a faint whisper in the dark. In cosmology, the smoking gun for inflation is the detection of primordial gravitational waves. These aren't just any gravitational waves like those detected by LIGO from colliding black holes. These are ripples in space-time created during inflation itself, relics from the universe's earliest moments. Think of them as cosmic echoes, vibrations from the Big Bang that continues to reverberate today. Inflation predicts that the rapid expansion of the universe would have generated a background of gravitational waves, stretching and squeezing space-time in a way that would leave a unique imprint on the cosmic microwave background. These waves are a consequence of the quantum nature of gravity itself. They represent the ultimate validation of the inflationary scenario. These primordial gravitational waves are different from the gravitational waves that have been observed from black holes. Those have a specific source, the merger of two massive objects. What we're looking for are gravitational waves that have existed since the dawn of time. Detecting these waves isn't easy. They are incredibly faint, and their signal is buried deep within the noise of the CMB. It's like trying to hear a pin drop in the middle of a rock concert. But scientists have devised a clever way to search for them by looking for a specific pattern in the polarization of the CMB light. Polarization is the direction in which light waves vibrate. Normally, light vibrates in all directions, but when light interacts with certain materials, it can become polarized, vibrating in a specific direction. The polarization of the CMB can be broken down into two components, E modes and B modes. E modes are generated by density fluctuations, the same fluctuations that gave rise to galaxies and galaxy clusters. B modes, on the other hand, can only be generated by gravitational waves. The existence of B modes in the CMB would therefore be a smoking gun for primordial gravitational waves and direct proof of inflation. Think of it like ripples in a pond again. If you drop a pebble into the pond, you'll create ripples that spread outwards in a circular pattern. These are like E modes, but if you were to somehow shake the pond from side to side, you would create ripples that are more complex and swirling. These are like B modes, the smoking gun signature of primordial gravitational waves. The search for B-mode polarization in the CMB has become a major goal of current and future cosmological experiments. Scientists are building increasingly sensitive telescopes, both on the ground and in space, to map the polarization of the CMB with unprecedented precision. They are building on the work of people like George Fitzgerald Smoot III. These experiments face enormous challenges. The B-mode signal is expected to be extremely faint, and it can be easily contaminated by other sources of polarization, such as dust in our own galaxy. It's like trying to find a single grain of sand on a beach that stretches to the horizon. The dust can mimic the effects of B-modes, so it's a challenge to tell if the source is gravitational waves or interstellar dust. But despite these challenges, scientists are making steady progress. They are developing sophisticated techniques to remove the foreground contamination and isolate the faint B-mode signal. They are refining their theoretical models, making more precise predictions about the expected properties of primordial gravitational waves. Detecting primordial gravitational waves would be a monumental achievement, a triumph of human ingenuity and scientific collaboration. It would provide definitive proof of inflation, confirming that the universe underwent a period of exponential expansion in its earliest moments. It would open a new window into the universe, allowing us to probe the physics of the inflationary epoch and test our understanding of quantum gravity. The detection of B modes would also allow us to better understand the conditions of the very early universe. What could the inflationary period tell us about the universe today? But perhaps even more importantly, the detection of primordial gravitational waves would inspire a new generation of scientists and engineers to push the boundaries of human knowledge and explore the mysteries of the cosmos. Perhaps this evidence can spark new life into those that have lost hope. Perhaps this is what the world needs. Imagine the headlines. Primordial gravitational waves detected, confirming inflation and revolutionizing our understanding of the universe. It would be a watershed moment in the history of science, a moment that would forever change our understanding of our place in the cosmos. And so the quest for primordial gravitational waves continues, driven by the unwavering curiosity and determination of scientists around the world. They are searching for the ultimate smoking gun, the definitive proof that inflation actually happened. Who will find them? Because if they exist, we are able to unlock so much more knowledge than ever before. This search holds more weight than any other research scientists are undertaking today. Its effect on mankind is unfathomable. And so, the quest for primordial gravitational waves continues, driven by the unwavering curiosity and determination of scientists around the world. They are searching for the ultimate smoking gun, the definitive proof that inflation actually happened. Because if they exist, we are able to unlock so much more knowledge than ever before. This search holds more weight than any other research scientists are undertaking today. Its effect on mankind is unfathomable. But what if, after all of this talk, after all of these elegant solutions, after all of these stunning images of the early universe, inflation isn't the only answer? What if the universe, in its infinite complexity, has more than one way to solve its cosmic riddles? Is it possible that there are other theories, other models, that can explain the universe's origins and evolution without invoking a period of superluminal expansion? It is as if you finally solved a Rubik's Cube only to realize that there are a handful of different algorithms to get you to the solution. The scientific process thrives on skepticism, on the relentless pursuit of alternative explanations, on the willingness to challenge even the most well-established paradigms. It is in the nature of every true scientist to question their own beliefs. It's how we advance our understanding, how we push the boundaries of knowledge, how we get closer to the truth, wherever it may lead. Perhaps the universe is more complex than we are giving it credit for. So, what are these alternative theories? What other possibilities are out there, lurking in the shadows, waiting to challenge the reign of inflation? Well, one of the most intriguing contenders is the cyclic universe model. Imagine, if you can, that the universe isn't born from a single Big Bang, but rather from a series of Big Bangs and Big Crunches, an endless cycle of expansion and contraction. It is a never-ending loop. In this model, the universe expands for a time, then eventually slows down, reverses direction, and collapses in on itself, crushing everything into a singularity. But instead of simply disappearing, the singularity rebounds, triggering a new Big Bang and a new cycle of expansion. It is a constant cycle of birth and rebirth. It is as if the universe has a heartbeat. Think of it like a cosmic accordion, constantly expanding and contracting, playing an endless tune. Each cycle wipes the slate clean, erasing the traces of the previous universe and setting the stage for a new one. In this scenario, the universe has neither a beginning nor an end. It has simply always existed, cycling through these phases of expansion and contraction for eternity. Now you might be wondering, how does this cyclic model address the problems that inflation solves? Well, the details vary depending on the specific version of the model, but in general, the cyclic model relies on a different set of mechanisms to smooth out the universe, dilute unwanted relics, and generate the seeds of cosmic structure. It uses a new set of variables. Another intriguing alternative is string gas cosmology. String theory, for those unfamiliar, is a theoretical framework that attempts to unify all the fundamental forces of nature into a single, consistent picture. Instead of point-like particles, string theory proposes that the fundamental building blocks of the universe are tiny, vibrating strings. These strings have different vibrational modes. Each mode corresponds to a different particle, like a note on a violin string. String gas cosmology applies string theory to the early universe. It proposes that the early universe wasn't filled with a smooth, uniform fluid, but rather with a gas of these vibrating strings. These strings would have interacted with each other, creating a complex and dynamic environment. They would collide and interact and do all sorts of things that particles do today. In this scenario, the expansion of the universe is driven not by an inflaton field, but by the energy density of the string gas. As the strings interact, they can wind around the dimensions of spacetime, preventing them from expanding. But as the universe expands, some of these dimensions become unstable and begin to grow rapidly. This is like stretching a rubber band. At some point, the tension causes the rubber band to snap. String gas cosmology offers a different perspective on the origin of the universe, one that is deeply rooted in fundamental physics. It provides a framework for addressing the problems of the Big Bang without invoking inflation. It has its own unique set of characteristics. These are just two of the many alternative theories that are being explored by cosmologists today. They may not be as well known or as widely accepted as inflation, but they represent a valuable reminder that scientific progress relies on testing theories rigorously and exploring other possibilities. It is important to never put all of our eggs into one basket. The quest to understand the universe's origins is a journey, not a destination. It's a process of constant refinement, of challenging assumptions, of pushing the boundaries of human knowledge. And while inflation may be the leading paradigm today, it's not the only answer. There may be other answers that we have not yet found. The universe is filled with infinite possibilities. Which brings us to the next question. What does the future hold? What new experiments and observations will help us to probe the universe's earliest moments and test the predictions of inflation and its alternatives? But what if there's more to the story? What if inflation, as successful as it is in explaining so much about the universe, isn't the only possible answer? Are there variations on the theme, alternative inflationary scenarios that could better fit the data? Or perhaps, even more radically, are there completely different theories that could explain the universe's earliest moments? It's a question that lingers in the minds of cosmologists, a nagging doubt that fuels the relentless pursuit of knowledge. The scientific process thrives on skepticism, on the willingness to challenge even the most well-established paradigms. So, with all of these theories and with so much that we don't know, where do we go from here? How do we truly probe that first second, that infinitesimal moment in cosmic history that holds the secrets to our very existence? The answer, perhaps unsurprisingly, lies in the future. In the next generation of telescopes and cosmological surveys, instruments designed to peer deeper into the universe than ever before, to capture faint signals from the dawn of time. Imagine building a time machine, not to travel through time itself, but to travel back in time by observing light that has been traveling for billions of years. That is essentially what these future telescopes are designed to do. They are designed to capture the most distant light from the earliest galaxies that have ever existed. The Simons Observatory, for instance, is a collaboration of scientists working to observe the cosmic microwave background from the high Atacama Desert in Chile. It is no easy task, involving a number of scientific minds that will come together to figure out exactly where we came from. The Atacama Desert is one of the driest places on Earth, the perfect location for a CMB observatory. The dry air minimizes the absorption of microwave radiation, allowing for clearer observations. The observatory is composed of a number of telescopes that scan the sky for the faintest signals. And then there's CMB Stage 4 or CMB-S4, a more ambitious project that aims to deploy even more telescopes at multiple locations around the world, including the South Pole. These telescopes will be equipped with thousands of detectors, each sensitive to different frequencies of microwave radiation. It is one of the most ambitious projects ever conceived. It is a plan to find something that could be something that's not even there. That is exactly what scientists are hoping to find. CMB-S4 promises to be a game-changer in cosmology, providing the most detailed map of the CMB ever created. So, what are these future cosmic explorers hoping to find? What secrets are they trying to unlock from the first second of the universe's existence? The answer, in a word, is precision. A refined measurement is what scientists hope to gain. These new experiments are designed to probe the inflationary era with unprecedented precision, to test the predictions of inflation and its alternatives with far greater accuracy than ever before. They aim to refine measurements of inflationary parameters, such as the energy scale of inflation, the shape of the inflaton potential, and the amount of primordial gravitational waves. It's about finding something that no one else can see. But perhaps the most exciting goal of these future experiments is the search for primordial gravitational waves, that elusive smoking gun that would definitively confirm inflation. Detecting these waves through their subtle signature in the CMB polarization would be a monumental achievement, a triumph of human ingenuity and scientific collaboration. It would require minds coming together from all walks of life. But beyond the search for gravitational waves, these future telescopes will also provide valuable insights into other aspects of the early universe, such as the nature of dark matter, the properties of neutrinos, and the formation of the first stars and galaxies. They aim to provide all of the missing pieces of the puzzle. It is about creating something that has never been done before. Imagine building a telescope so powerful that you can see the first stars being born, that you can witness the formation of the first galaxies. That is the ultimate goal. These are the mysteries that are still eluding us to this day. These upcoming experiments aren't just about confirming or refuting existing theories. They also have the potential to reveal completely new phenomena, to uncover unexpected surprises that could revolutionize our understanding of the cosmos. It's about being able to say that we figured it out, that all of the hard work that everyone contributed was worth it in the end. Perhaps they will discover new types of particles, new forces, or new dimensions of spacetime. Perhaps they will find evidence for a multiverse, for other universes beyond our own. The possibilities are endless, limited only by our imagination and the laws of physics, or perhaps even by laws of physics we do not yet know. What we have been taught is just not correct. The quest to understand the universe's origins is a never-ending journey, a continuous cycle of exploration, discovery, and refinement. Each new experiment brings us closer to the truth. Each new observation challenges our assumptions and forces us to think in new ways. It is a labor of love that requires everything to fall into place. These experiments are the key to unlocking some of the biggest questions that we have as humans. How did everything begin? Will there be an end? Are we alone? These experiments can begin to help guide us towards the answers. These future telescopes and surveys represent a bold step forward in our quest to understand the universe's earliest moments. They are a testament to human curiosity, ingenuity, and the unwavering desire to explore the unknown. It is the culmination of hundreds, if not thousands, of years of thought, research, and exploration. Within roughly the first 10 to the minus 32nd seconds, inflation occurred. This fleeting instant fundamentally shaped the universe's subsequent 13.8 billion years of evolution. Its brevity belies its profound and lasting influence on cosmic destiny. The influence it has had on everything is unfathomable. So what secrets will the next generation of cosmic explorers uncover? What new wonders await us in the depths of space and time? As we stand on the cusp of a new era of cosmological discovery, the possibilities seem limitless, and the answers perhaps are closer than ever before. These future telescopes and surveys represent a bold step forward in our quest to understand the universe's earliest moments. They are a testament to human curiosity, ingenuity, and the unwavering desire to explore the unknown. Within roughly the first 10 to the minus 32nd seconds, inflation occurred. This fleeting instant fundamentally shaped the universe's subsequent 13.8 billion years of evolution. Consider that for a moment. Less than a trillionth of a trillionth of a trillionth of a second, an incomprehensibly small fraction of time. Yet within that infinitesimal moment, the universe underwent a transformation that continues to reverberate today. It's a time scale that makes the blink of an eye seem like an eternity. How could something so brief have such a profound and lasting influence on cosmic destiny? It sounds almost impossible, doesn't it? Imagine trying to capture a single frame from a movie that lasts for more than a century. That single frame, however, contains all of the information needed to explain the entire story. That is the weight of the inflationary time scale. It holds the beginning of all things. Perhaps the better question is not, how could so much happen so quickly, but what conditions allowed it to happen at all? What were the initial ingredients, the primordial forces, that conspired to create such a cataclysmic event? It's like trying to understand the explosion of an atomic bomb by studying the individual atoms that make it up. The power lies not just in the components, but in the way they are arranged and the forces that bind them. Think of it like a seed, a tiny, insignificant speck that contains all of the information needed to grow into a giant redwood tree. The seed itself is small and simple, but it holds the potential for immense growth and complexity. Inflation was like that seed, a tiny kernel of existence that contained the potential for the universe we see today. Or perhaps consider a musical note, a single vibration of air that can evoke a range of emotions, from joy to sorrow, from peace to excitement. That single note is small and fleeting, but it can have a lasting impact on our souls. In a similar way, the inflationary time scale is like that single note, a fundamental vibration in the fabric of space-time that set the tone for the entire cosmic symphony. The sheer brevity of inflation belies its profound and lasting influence on cosmic destiny. It's a reminder that even the smallest events can have enormous consequences. A single butterfly flapping its wings can theoretically cause a hurricane on the other side of the world. It's also a humbling reminder of how much we still don't know about the universe. We are only beginning to scratch the surface of understanding the inflationary epoch. What the universe has in store for us is unfathomable. It forces us to ponder the very nature of time. It begs the question of whether there even was a beginning and an end. Or are these all constructs that have been made up by mankind? And so, we stand at the edge of understanding, gazing back at the very moment of creation. That fleeting inflationary period, a cosmic hiccup in the grand scheme of things, somehow managed to set the stage for everything that followed. From the swirling galaxies to the very atoms that make up our bodies, it all has its roots in that unimaginably brief burst of expansion. But what does it mean to us, as humans, to understand this? Consider the sheer scale of it all. 13.8 billion years of cosmic evolution, all stemming from a period lasting less than a trillionth of a trillionth of a trillionth of a second. It's a bit like watching a single domino fall and trigger a chain reaction that topples structures across the entire planet. The initial event is almost insignificant, but its consequences are far-reaching and profound. Inflation provides us with a compelling narrative for the universe's earliest moments, a story that weaves together the threads of quantum mechanics, general relativity, and observational cosmology. It explains why the universe is so vast, so flat, and so uniform. It explains why there are galaxies, stars, and planets, and ultimately why there is life. It's a narrative that just a few decades ago would have been relegated to the realm of science fiction. But now, thanks to the tireless efforts of scientists around the world, it's a narrative that is firmly grounded in observation and experiment. But inflation is more than just a story. It's a lens through which to view our vast, flat, and intricately structured universe. It allows us to see connections that were previously hidden, to understand the relationships between the smallest particles and the largest structures. It is a reminder that we are all part of something much larger than ourselves, a cosmic web that stretches across billions of light years. It's a reminder that we are star stuff contemplating the origin of star stuff, to borrow a phrase from Carl Sagan. We have the capacity to reflect, to think about what our meaning is, and whether we can truly understand what is happening around us. We are able to comprehend that the very elements that make up our bodies were forged in the hearts of dying stars billions of years ago. And now, we are using those same elements, our brains, our instruments, to unravel the mysteries of the cosmos. It's an incredibly strange loop, a cosmic Ouroboros consuming its own tail. Inflation challenges us to think beyond our everyday experience, to grapple with concepts that seem almost impossible to comprehend. It forces us to confront the limitations of our own intuition, to push the boundaries of human knowledge and imagination. It is a task that has been undertaken by many minds throughout history. It is a task that we continue to work on today, and it is a task that may continue forever. It demonstrates the ingenuity of what we can do. As much as there are terrible things that can happen, we have also done some incredible things, and we will continue to do so. The question is whether we can put aside our own selves and help propel human civilization as a whole. Inflation is a perfect example of that. But even with all of the progress we have made, there are still things that we cannot yet answer. How do we know it is correct? What if it is all an elaborate hoax? The truth is that scientists are constantly trying to find out the answer. To question what they believe in is what makes a true scientist. If we are unable to do that, then what hope do we have? Even the most successful scientific theories are ultimately just models, approximations of reality that are subject to revision and refinement. There will always be mysteries to solve. There will always be new questions to ask. The universe is simply too complex, too vast, too strange to be fully understood by any one person or any one generation. Perhaps what we see is not real. Perhaps we are simply pawns in some elaborate game. We may never know, but that doesn't mean that we shouldn't stop looking. But that's okay. It's precisely this sense of mystery that drives us forward, that fuels our curiosity and inspires us to continue exploring the cosmos. What began as a search for the very origins of life is now turning into an all-out space race. The great thing that will be gained is more knowledge and exploration. As we gaze into the future, into the eyes of exploration, we are beginning to find more and more answers, but those answers give way to even more questions. The universe may never tell us everything, but that will not stop us from trying to listen to every single word that it has to say. What secrets will future generations uncover? What new wonders await us in the depths of space and time? The universe is an enigma, but we have the power to uncover what is in the very fabric of time and space.